Welcome everybody online, and welcome back those of you who are here. Santiago will be the host, but there are a couple of minor announcements, if I may. We've been alerted to the fact that the train to the airport is not running this Saturday. Must be repairs of some sort. So if you could make a note of that, but I believe that there are buses running from Union Station, but you need to go online and just double check that. So please be aware of that. Please be aware of that. Okay, you can do that. There are clay lectures next week by Oscar Randall Williams. We hope many of you will be able to stay for those. There are 3 lectures on Monday, Tuesday, and Wednesday. And the other announcement is we are now nearing the point where if you want to go to the banquet, the dinner tonight, you need to pay, but the bank is closed at the minute. But please try not to mob me when the bank opens, because I make mistakes. And if you could just have one at a time, I'll be here all day and you'll be able to pay. Santiago got a discount, right? Santiago.
I owe you 3.
Welcome, Santiago.
Okay. Good morning. Today, Ralph is going to tell us about his remembrance of his work with Fred. I spent some time trying to find something in the internet about the relation between Ralph and Fred, and I couldn't find a word. Not in Wikipedia, Scholar, Math Science Net, nothing. So we're going to hear something with many secrets.
Yeah, many secrets.
And we're very lucky to be able to hear this story about the relation between 2 such great mathematicians.
Thank you. Do I need? I don't. Can you hear me? Yeah, it's a pleasure and an honor to be here at this conference honoring Fred. What I'd like to talk about are several topics of old research, much of which was joint with Fred, but as I wrote, all of it was inspired by him. And so what I'd like to do, actually, is start with a quote from Mark Mahowald. I think Mark had a great influence on both Fred and I. So this was from a Northwestern topology seminar in 1979. And Mark started off by saying, he was giving the talk, and he started off by saying, let's discuss the first odd dimensional sphere, S2. And the really funny thing about that was, I think everybody in the audience knew what he was talking about. From Mark's point of view, what was interesting about a space was its homotopy type, and in particular, its homotopy groups. And from that point of view, the circle's just not all that interesting, the first odd dimensional sphere. And if you're going to study the next one, S3, you might as well study S2. And that's, of course, because of the Hopf vibration. So you know that S3 and S2 have the same homotopy groups, dimensions 3 and larger. And of course, there's another way of saying this that I think appealed to Fred more. And he would take the twofold loop map of the Hopf map. So that's a map from, let's see if we get this pointer to work. Yeah. From loops 2S3 to loops 2S2. And from that, you immediately see that pi 0 of loops 2S2 is the integers corresponding to the degree of the self map of S2. But each path component of loops 2S2 is homotopy equivalent to loops 2S3. So if you're going to study loops 2s3, you might as well study loops 2s2 and vice versa. And so what I'm going to discuss in this talk are several problems that have to do with loops 2 of S3 in one way or another. And for sure, this was one of Fred's favorite spaces, and certainly one of mine. Okay, so the first topic I want to mention is an old one, bundles over configuration spaces and braid orientations of manifold. So let me start by getting some notation down. Pretty standard, I think. FRNK will be the configuration space of K ordered points, and Rn. BRNK will be the quotient by the three symmetric group actions. So these are K unordered points. B sort of stands for braid, often referred to as braid spaces. And the reason for that, of course, is and a very important example is when n equals 2. These are k pi 1s for the braid group. And when n is infinity, it's a k pi 1 for the symmetric group. Again, some more notation. So for base space, let Cn of x be configurations of points in Rn across x to the k mod divided by the symmetric group, and modulo a base point relationship. And there's a map to loops n suspension n x, which is an equivalence when x is connected. One of the basic theorems of iterated loop space theory. You can think of these spaces as configurations of unordered points in Rn, each having a label in by a point in x. And if that point in x happens to be the base point, you just throw it out. And that's what the base point relation is. A little bit more, again, getting notation straight. A related construction is you can take BRNK and map it to BRNK plus 1. And you can take the homotopic colimit, call that BRN infinity. And there's a map to a path component of loops n Sn. The lowercase 0 means that take the path component of degree 0 maps. That's where the base point lives. And the theorem is that induces an isomorphism in homology. For n equals infinity, this is an old theorem of Barrett, Pretty, and Quillen. For general n, it's in Fred's thesis. I think Arnold in Russia also had a proof of this. I'm not sure about that, but I know he studied the homology of these braid spaces. So in the case when n equals 2, BR2 infinity is homology equivalent to loops 2s2, which is our favorite space, loops 2s3 again. Now, these spaces have interesting vector bundles over them. You just take configurations of points across R to the k. That gives you a k-dimensional bundle that I'll call CNK. And you can write down their classifying map. They're very natural. You just take BRNK, map it to BR infinity K. That's a classifying space, as I mentioned, of the symmetric group, and you think of the symmetric group as inside the orthogonal group. And that's the classifying map of these bundles. Now, one thing Fred did, together with Mark Mahowald and Jim Milgram, was when n equals 2, he showed that the order of these bundles is 2, meaning you take the Whitney sum of the bundle with itself, it becomes trivial. I kind of wanted to show you a quick proof of this due to Ed Brown, a napkin proof that he showed me when I was a student. But I found out that this talk was 45 minutes, so perhaps somebody will ask a question about it, right? Okay. Now, the order in general of these bundles. Again, how many times does it take when you add it to itself before it becomes trivial? For general N, it was computed in a paper by Fred and myself. Nick, I was just a postdoc. Nick was a graduate student in Chicago at the time, and Joe Neisendorfer. So let me tell you what we proved and what we couldn't prove. So let me define a number, A and K. And A and K will be described by its prime decomposition. The order, the exponent of the prime 2 is rho of n minus 1, where rho of m is the number of positive integers less than or equal to m that are congruent to 0, 1, 2, or 4 mod 8. Numbers come up in vector fields on spheres, atoms, old work. The exponent of an odd prime is just n minus 1 over 2, integral part of that. And so we computed the order 3/4 of the time. Namely, if n is not divisible by 4, we proved that A and K is the order of these bundles. We wanted to prove that in general, but all we could prove when n is congruent to 0 mod 4 is that A and K divides the order, and the order divides twice it. So there's a factor of 2 that we couldn't resolve back then. Just yesterday, I guess, Nick told me he thought it was resolved by now, and he thought maybe it was even resolved by Fred. So
is this a stable computation or an unstable?
It's actually stable.
yeah, this is a stable computation. Okay. There's a couple remarks about this result. In the case when you have 2 points in Rn, that bundle is easily seen to be stably isomorphic to the canonical line bundle over Rpn minus 1. It's actually the line bundle plus the trivial bundle. And so the fact that the order is 2 to the rho of n minus 1 is a classical result of the atoms. A fellow, Su-Win Yang, who was a student when I was a student of Ed Brown, he computed the order of these bundles when you had p point, p being an odd prime. And he proved in general that A and K divides the order. And the conjecture that the order was or is A and K was made by him as well as Mark and Fred. The idea of the proof, I want to just mention quickly, is that to show that the stable classifying map, and by that I mean the map to BO as opposed to BO to K, factors as a composition of maps, and one of which is the inclusion of loops n Sn into loops infinity S infinity, a particular component. And then studying the order of that inclusion map using the results of Fred, John Moore, and Joe Neisendorfer on exponents of unstable homotopy spheres. That was done just a few years prior to this. I think that's all I want to say about that particular result. But I want to go back and look at that classifying map again. In the case of n equals 2, in the k pi 1 for the Braid group to BO. And again, using basic iterated loop space theory, there's another way to describe this map, which is quite useful. Namely, you can look at the R2K, so that's classifying space of the Braid group. Let K get big, taking the homotopy co-limit, so what I'm calling B of beta infinity. As I mentioned before, that's homology equivalent to loops 2s2, which is loops 2s3. Oh, sorry. Let's see which button. Yeah. And there's a map from loops 2s3 to BO, where loops 2s3 is twofold loop space. It's, if you like, in a sense, the free twofold loop space generated by a circle. So it's this eta tilde is the unique twofold loop map that extends the map on S1 that generates I1 of VO, which is Z mod 2. Said another way, same way really, is that it's the unique twofold loop map that is non-trivial on the fundamental group. So that's another way of describing the stable classifying map. Let's look at the homology of these maps and these spaces. The homology of the classifying space of the infinite braid group, which, as we said, is the homology of loops 2S2 or the homology of loops 2S3, is a polynomial algebra, and I'm always taking homology with Z mod 2 coefficients. It's a polynomial algebra on infinitely many generators. Each of it has dimension 1 less than a power of 2. That's in Fred's thesis. Again, I think also proved by Arnold. That's all I want to say about that, except for that fact that we've seen that algebra before. That algebra is the same as the dual of the Steenrod algebra, Milner's famous calculation. Usually it have different names. But again, it's the polynomial algebra on class of dimension 1 less than the power of 2. So which of course is the homology of the Eilenberg-MacLane spectrum. So it's natural to ask, how is this infinite braid group or loops 2S3 related to the Eilenberg-MacLane spectrum? And the answer turns out to be through Thom spectra. Namely, we have this map that I talked about, this twofold loop map that's non-trivial along the fundamental group, and I called it eta tilde, and let M of eta tilde be the Thom spectrum of that stable bundle. And then a theorem of Mahowald that was written down in a paper of Stuart Pretty is that this Thom spectrum is an E2 ring spectrum, and that's just really because this map is a twofold loop map. Localized at the prime 2, it's Eilenberg-MacLane.
Equivalent as,
Sorry?
equivalent as what?
So as two local spectra.
No, not preserving.
Yeah, it is. Yeah. So that's a really cool theorem, that the Eilenberg-MacLane spectrum appears as a Thom spectrum. So, you know, you could pull that back to the braid group and look at the composition of the map from the classifying space beta infinity, the infinite braid group. And Fred proved that that Thom spectrum is Eilenberg-MacLane as well. That's not a surprise because, as we've been saying, the infinite braid group has the same homology as loops 2S3. But it has a really cool geometric consequence that I wanted to point out, and Fred pointed out in his Inventiones paper. So, you know, classical result of René Thom is that every Z mod 2 homology class is represented by a manifold, because MO is a wedge Eilenberg-MacLane spectrum. But this result says you can take that manifold to be braid oriented, meaning the structure group of its normal bundle, stable normal bundle, is reduced to the braid group. Now the braid group, of course, is a discrete group. So every mod 2 homology class is represented by a manifold with a discrete structure group. Manifolds with discrete structure groups have flat connections. So a consequence is that every mod 2 homology class can be represented by a manifold with a flat connection. Very cool result coming from this homotopy theory. Now this Thom spectrum, M of C2, that is an Eilenberg-MacLane spectrum, it's built like all Thom spectra are. It's built out of good old-fashioned Thom spaces of finite dimensional bundles. And that's these bundles that we've looked at before, C2K. And this Thom space is just given by configurations of points in R2 across S1, but now smash product K times. So you can ask, well, what can you say about the homotopy type of these Tom spaces, where you know the homotopy type of the Tom spectrum that they build up? And I think I'll just jump to the result. So remember, the cohomology of the Tom spectrum is the Steenrod algebra. So the cohomology of these Tom spaces are actually cyclic modules over the Steenrod algebra, whereas the module you get by dividing out by the left ideal generated by chi square I, 2I bigger than k. Chi is the canonical anti-automorphism. And Mahowald calculated that, and people he recognized, and other people recognized, we've seen these modules before. These modules are the so-called Brown-Gittler modules, because they're the cohomology of the so-called Brown-Gittler spectra. Brown-Gittler spectra are characterized up to homotopy, or up to two local homotopy, I should say, by two properties. One is what their cohomology is, and the other is, if you look at the generator of the cohomology viewed as a map to McLean, then that induces a map in generalized homology theories, with the target being ordinary mod 2 homology. Then that map is always surjective in a range of dimensions. That's a statement about a collapse of an atom spectral sequence. I didn't quite say it that way. The corollary, and this is the way they did say it, is that if you have a manifold, a closed manifold of dimension n, and you look at its Tom spectrum of its stable normal bundle. Now, as you know, Tom's spectrum can be suspended or desuspended. So I want to normalize this so that the Tom class is in dimension 0. And there's a lifting from the Tom spectrum of the normal bundle, that manifold, to Bn, a lifting of its Tom class. And that result was important in the Brown-Peterson-Gittler program for studying emergence manifolds, the immersion trajectory. So that's where that came from. And by the way, that property follows very quickly from the property I described before about the atom spectral sequence for any space, just because of the Spanier-Whitehead duality of a manifold and the Tom spectrum of its normal bundle. Now, Mark conjectured that these Tom spaces built out of these bundles over braid groups were in fact Brown-Gittler spectra. He knew that they had the same cohomology, and that was proved by Brown and Peterson. So these Tom spaces have this interesting homotopy type. The Brown-Gittler spectra, again, localized. This fact was used by Mahowald when he constructed the so-called A to J family, which is an infinite family in the homotopy groups of spheres. And I'll say more about that in a few minutes. And how one can apply that to the Kervaire invariant problem. But I first want to study these spaces, these Tom spaces, built out of these bundles over the class-like space of braid groups. I want to study them a little bit more directly. I'm going to call them DK, just to use the notation a little bit. Yeah, they're involved in the study of rats. So, and what I mean by rats are spaces of rational functions, which are holomorphic maps from P1 to some smooth variety. You know, such spaces of rational mappings have been studied by algebraic geometers for many, many years, all sorts of different notation. When we started a project studying the topology of these spaces, Fred suggested the terminology, let's call them rat spaces. And that stuck, and this was in the mid-'80s or so. And ever since then, every paper I've seen on the topology of rational function spaces or holomorphic mapping spaces refers to them as rack spaces. So let me make a definition. Rack K is the space of base rational functions of degree K. So quotients of polynomials, complex polynomials, and they can be viewed as holomorphic maps from CP1 to itself of degree K. Based, you have to choose a base point condition. It doesn't really matter. But for convenience, we chose a mapping the point at infinity. You know, thinking of P1 as C union infinity, mapping the point infinity to the number 1. And the reason you choose that is then when you're talking about a rational function as a quotient of polynomials, you can think of them as a quotient of monic polynomials. Now, a monic polynomial, as you all know, is determined completely by its roots. So to study these rational function spaces, it's a configuration space right up Fred's alley. It's a configuration space of roots and poles. The roots and poles can be anything, including higher multiplicity, but none of the roots can equal any of the poles. And that's because if they did, then the holomorphic map would have degree lower than K. The first theorem, I think, or the first significant theorem on the algebraic topology of these moduli spaces of rational mappings was proved by Siegel. In modern language, you can call his theorem a homological stability theorem. He showed that the homology rack K and rack K plus 1 agree up through a range of dimensions. And if you take the homotopy co-limit, then you get a homology equivalence with loops to S2. And what does that map? Well, as I said, rational functions are holomorphic maps from degree from P1 to P1. And so you're just thinking of a holomorphic map as a continuous map. So it gives you a map, and they're base maps, so it gives you a map to loops to S2. And it's really a beautiful result and a precursor of many, many theorems along the lines of, here's a moduli space defined by some algebraic conditions or maybe a differential equation. And in some kind, and often in a homotopy co-limit over some kind of index, they become homology equivalent to the configuration space that these differential equations are defined upon. And this was perhaps one of the first results along those lines. Let me tell you what we did. First, maybe a little bit more notation. We have these spaces Cn of x that I mentioned earlier. They're naturally filtered spaces, and I can look at the subquotients of the filtration. And the famous stable splitting theorem says that stably Cn of x is equivalent to the wedge of the subquotients of that filtration. So in particular, loops n, assuming x is connected, loops n suspension of x stably breaks into these pieces. Fred was involved in an improvement on Snaith's proof. He proved something stronger together with Larry Taylor and Peter May. I had a contribution as well. But so this is an extremely important theorem in iterated loop space theory and stable homotopy. And in the case when x is S1 and n dimension of the space that you're taking configurations in is 2. So we're back at these spaces where we know the cohomology, we know a lot about their homotopy type, their Brown-Gittler spectra, and so forth. We can identify the stable homotopy type of the rational function space. Namely, the stable homotopy type of rack K is you take the first K of the terms in the Snaith decomposition. So again, that tells us directly what the cohomology is. It's a direct some with cyclic modules over the scheme rod algebra. Again, since these spaces are Brown-Gillis spaces, we know a lot about their homotopy type. So that was a theorem that Fred and I and Ben Mann and Jim Miller worked on. It was really quite a fun collaboration. We also proved a similar theorem identifying the stable homotopy type of what Fred called RAT-K of CPN, meaning holomorphic maps from P1 to Pn, where the spaces involved in splitting were the subquotients in the snake filtration with the 2n-1 sphere replacing or taking on the role of the circle in the system. Okay, I want to go to the last topic I want to discuss, and so it's loops 2s3 and the Kervaire invariant 4 problem. Kervaire invariant 1 is old hat now by the work of Phil Hopkins and Raphael, so I want to talk about the Kervaire invariant 4 problem and the role of loops 2s3, or a role of loops 2s3 in that. Mark Mahowald defined a stable map from loops 2s3 to the sphere spectrum. So let me call that construction map. I see that I've changed the notation. I apologize. So Q of S naught is what I called loops infinity S infinity a few minutes ago, and we'll let K of S naught be the component of maps of degree K, self maps of spheres. Q1 of S naught are self maps of degree 1, and that's often called G in the literature historically. Some cases referred to as F. But the interesting thing about Q1 of S naught is that it is an infinite loop space, the basic product being composition of maps. You compose two maps of degree 1, you get a map of degree 1. So we want to use that in a very similar construction to what we did a few minutes ago. Namely, let eta be the generator of pi 1 of that component. Well, that's the stable homotopy groups of spheres, so that's C mod 2. So eta is the generator. And since Q1 of S naught is an infinite loop space and its structure, I can extend that to a map, a unique map of loops 2s3 to Q1 of S naught. That is non-trivial on the fundamental group. Very similar to what we did before with DO instead of Q1 of S naught. And I'm calling that eta hat. Now, I want to extend it to a map, a base point preserving map. So give loops 2s3 a disjoint base point and send that disjoint base point to the base point of Q of S naught, which lives in the component degree 0. And so you get you can take its adjoint and some map of spectra that Mark studied. And by construction, it's a map of ring spectrum. And remember, we have the state splitting of this spectrum. We actually have an extra copy of the sphere spectrum because we add the disjoint base point. But it splits into these spaces coming from braid groups. And we know their cohomology. We know a lot about their homotopy type because they're Brown-Gillis spectrum and so forth. We'll add GK from one of these pieces, one of these Brown-Gillis spectra, look at the sphere spectrum of the induced map. Now, one thing Mark did right away is that if you looked at the component d2 to the I, power of 2, and you looked at the mapping component, this is my notation, the sphere spectrum, this is a stable mapping component, homotopy profile of the map. He showed that there was a non-trivial scheme rod operation in that mapping component that took the bottom dimensional class that are called sigma naught up into, it turns out to be the very top dimensional class. But in particular, it implies that this map, G2 to the I, is non-trivial in homotopy. is what those of us of a certain length in our teeth would call a functional squaring operation, a functional cohomology operation. So this map was detected in that way. Now, there is a more cleaner way of saying that, and I'm not going to go into the notation and details, but roughly speaking, it says that that map from D2 to the I to the sphere spectrum is viewed as an element of cohomotopy. So there's an atom spectral sequence converging to the cohomotopy, and it's represented by HI plus 1 in the appropriate way. It's the relationship between the squaring operations in the power of 2 and the HI. Okay, hang in there with me now. Now we want to use the fact that this D to the I is a Brown-Gittler spectrum. And remember, one of the property that Brown and Gittler were interested in is that if you took any n manifold, the Thom space of the normal bundle maps to the Brown-Gittler spectrum. So the map from the Thom space or Thom spectrum of the normal bundle of RP2 to the I to this Brown-Gittler spectrum. And so by composing, we get an element in the cohomotopy of the Thom spectrum of the normal bundle of projector space. And again, it is detected by an HI plus 1. Just did this so that we're in the realm of manifolds. And again, using the Spanier-Whitehead duality of a manifold in the Thom spectrum normal bundle, a cohomotopy class becomes a homotopy class in the manifold itself. And we get a stable, an element in the stable homotopy groups of projector space. And you can map to RP infinity if you like. And it turns out, I don't want to emphasize this point, but these classes in the stable homotopy of RP infinity map to Moholy-Wald's eta, I should have called it J, the eta I family in the homotopy groups of spheres under the concrete map. So up until this point, this is just a slight modification of Moholy-Wald's original argument where he constructed this eta family. I want to push a little further. So let's take that element in the stable homotopy of RP infinity and project onto a stunted projector space. So I'm just taking that little baby RP1 at the bottom of RP infinity, squishing it to a point. And I'm calling that composition beta. So that should start people thinking about the variable. Beta tilde. And it's a fairly standard atom spectral sequence argument. In fact, you can use Adam's original paper on the non-existence of elements, Hopf invariant one, to show that that composition is represented by HI squared in the atom spectral sequence converging to its homotopy group. More like the Kervaire. Finally, I'll call an element theta I of SO2 to be in the homotopy groups in the Kervaire invariant dimensions, 2 less than the power of 2, of MSO2, the Thom spectrum of SO2 cobordism, to be the composition that you get by composing the map we had a moment ago to the stunted projector space to CP infinity, and then realizing that CP infinity is MSO2. In my conventions, it's actually the two-fold suspension of MSO2. And that gives you an element in the stable homotopy of MSO2. And with John and I, together with Mark Moholy-Wald's group, gosh, 40 years ago, was that these classes are represented by HI squared in the atom spectral sequence for MSO2. So what does it have to do with Kervaire invariant? Well, you know, this classical Pontryagin-Thom theorem, an element of stable homotopy of MSO2 represents a cobordism class of the way I'm describing it is a pair. You have a manifold in this dimension, 2 less than the power of 2. It's an oriented manifold. That comes from the S in MSO2. And it's immersed in codimension 2 Euclidean space. That's the 2 in MSO2. So the homotopy of MSO2 can be viewed as cobordism theory of oriented manifolds immersed in codimension 2 Euclidean space. So there are these manifolds.
Wait, when you say immersion, their terms involve embeddings. Stable homotopy involves immersions.
So I'm trying to remember who might have made this observation, but the homotopy of an MOK or MSOK is cobordism classes of immersions into codimension K.
The stable homotopy.
Yeah.
Yeah, that was
Oh,
Well-
the unstable homotopy.
Huh?
That's absolutely, that's right.
right. That's the point.
Yeah.
Wells, Robert Wells, Stephen Miller.
Absolutely. So, so the question of is an immersion regularly homotopic to embedding, sometimes in a range of dimensions is going to be translated into there's a stable homotopy class coming from an unstable.
So the reference really involves this much the later work of the Stephen Miller. It's not from Pontiac.
Oh,
Okay, that's what I
you're
meant.
right.
I mean,
You're right. Sorry. Yeah, I should have said more about that. But yeah, absolutely. So it's immersed in a codimension 2 Euclidean space. And that's could be better. Could be immersed in codimension 1 Euclidean space. And if it were, it would have a framing because of the very deep reason that SO1 is open. So it would say, if it immersed into codimension 1, it would say that the stable normal bundle has structure group trivial, namely a framing. Well, that was pretty exciting to us. We thought, these constructions are fairly concrete, homotopy theoretically. Maybe we can use these constructions to actually construct manifolds, immersed in codimension 2 space. If we push it real hard, maybe we can get them into codimension 1 Euclidean space. And then, unfortunately, Phil Hopkins and Rapnell came around 20 years later. But I'll say more about that in a minute. But what does this have to do with the Kervaire invariant? This has all been stable homotopy so far. Now, if you go back and read Browder's paper, where his major paper on the Kervaire invariant discusses how the existence of elements of Kervaire invariant 1 is equivalent to HI squared being an infinite cycle of the atom cycle sequence. The essential agreed that allows one to define the Kervaire invariant, you don't need the framing, but what you do need is a trivialization of certain Wu class, characteristic class. And Ed Brown carried this idea further, and he actually defined a Z mod 8 value Kervaire invariant for any cobordism theory that has a vanishing Wu class. And if you go to the classical place where Kervaire and Miller studied frame cobordism, it takes values of in Z mod 2 inside of Z mod 8, 0 and 4. So that's where the Kervaire invariant 4 comes in. And what we proved in that same paper is we proved a Browder type theorem, or really it wasn't much more than noticing that Browder's argument proved something stronger, that is basically the equivalent of the existence of manifolds of Kervaire invariant 4. In other words, those that at least potentially could have been in the image of frame cobordism. the equivalence of that question with elements in the from the atom spectral sequence detected by hj squared. So that's one thing we did in that paper. And then from that, we could conclude that for every j equals j bigger than 0, there is an oriented manifold of the Kervaire dimension immersed in codimension 2 Euclidean space that has Kervaire gradient. So you do have this infinite family of non-trivial Kervaire invariants. And this is the best you can do in terms of immersion theory because of the theorem 20 years later of Phil Hopkins and Ravenel that says none of these manifolds can have gradients, at least for j bigger than psi. So that was really clear. Full water on my hopes.
So that shows Browder's theorem does correspond to something geometric.
Oh, absolutely. Yeah.
That's interesting.
Yeah. So if you, from our point of view, it corresponds to these variants we find on codimension 2 inversion manifolds. So let me end with a question from Mark's Hall. And this question came up in my very last conversation with Mark before he passed away several months ago. Now, what does that mean about how bigger equals 7, m has to be bigger or equal to 2, because if m equals 1, CP1
been muted.
Oh, my wife likes to do that a lot to me too. Anyway, I noticed that I can't remember what we were talking about then, but I see that I had a glass of wine, so I was enjoying that conversation, I know. And from the picture, I'm sure that I was trying to convince Fred of some argument or another, and he was having none of it. But anyway, like all of you, I miss Fred very much, and he had a great influence on me, like he has on our entire subject. Anyway, thank you very much.
Are there any questions? Questions?
So coming back to your first topic, you had these bundles, I think you call them CNK.
Yeah.
And I was wondering if you could explain why 2 is the hardest factor of their order to sort of understand. And also, you said that you think it's known, or Nick thinks it's known. And I was wondering if you could say a little more about that.
Nick, do you want to answer that question? No.
I just remember coming across some paper recent years where somebody actually used this paper that I can't remember the paper, but maybe start with math reviews and see who's referenced our paper, and you got some other papers. And I do remember Fred had some paper where he had some argument just, in the course of doing something and maybe resolve that particular thing. We had some sort of sneaky trick for
one thing that made it harder for us, just in the approach we took, was we relied, as I mentioned, in the work of Cohen, Moore, and Neisendorfer.
Right.
And as I remember, that was sort of much stronger at odd primes.
Well, yeah, that was the odd prime thing, right? And
Right.
2 is
So the
separate.
prime 2 was harder for us.
Because exponent results aren't known for prime 2.
Right.
Right.
So,
Or the best exponent, right?
Some other questions? Some questions from participants online?
one of them says, there seems to be some problem with the sound.
Andy might have a question.
Hmm?
Andy, I think Andy might have a question.
Andy?
No, I don't have any questions.
Hi, Andy.
Hi.
Okay,
Okay.
I'm done, right? Oh,
So I'm remembering back in the old days when before Hopkins. So Mahowald, given Browder's picture, assuming it were true, all those elements existed. He had these finite trees coming down from each element that describes the entire spectral sequence, atom spectral sequence.
yeah,
And
reference.
does this further conjecture lead to a further, slightly more complicated picture with m equals 2?
So others are better qualified to answer that than I am, but my understanding is that with new techniques, my understanding is that with new techniques having to do with motivic homotopy theory, like Dan Isaacson, where are you here? There you are. But and collaborators can get well beyond what Mark was talking about in those days.
But
Isn't that correct?
it was conditional, though. It was conditional on Browder's elements being realized. So I'm asking, since they're not realized because of Hopkins, does this next conjecture that m is 2, showing that they're all realized, imply positive further statements?
That's
like
a good
that?
question. I don't know the answer to that. Yeah. Yeah.
More question? Well, we cannot say that we know everything we wanted to know about the relation between Fred and Ralph, but thank you very much.
We resume when you hear someone clapping. Sorry?
In 18 minutes.
There you go. Thank you, Santiago.
Leave it on.
Okay. Yeah, so now I'm not muted, right?
No, right now you are not muted. Yeah, sorry.
Okay.
My bad.
Yeah, it's fine.
Can this
Okay.
go anywhere on your shirt?
Thank you.
And are you okay with your talk being recorded?
Yeah, thanks. Oh, thanks.
Thanks very much.
Thanks.
Before we start, there's an announcement to make. There will be a group photograph at the end of the next lecture. So at 12:30, when things are wrapped up for the morning, don't run off to lunch right away, because there'll be a group photo. It will be out there on just outside the doors there.
Oh, this, yeah. You can just say VU Amsterdam. You can say VU Amsterdam. Just the V.
No, I wanted
Okay.
to say this whole thing.
Okay. Vrije Universiteit Amsterdam.
Vrije Universiteit.
You think I'm joking?
Shouldn't be with a coffee cup. Okay, our next speaker is Invar Klang from Kervaire Universiteit, Amsterdam. Did I get it wrong?
Approximately.
Okay.
Okay. Right. Thank you. Yeah, it's great to be here. Ralph was my PhD advisor, and so loops to S3 is one of my favorite spaces as well. But today I'm going to, unfortunately, loops to S3 is not going to show up in this talk. So I'm going to talk about isovariant homotopy theory. And so maybe I'll start by, so this is a joint ongoing sort of series of projects with Sarah Yackel. And I'll start by sort of just like explaining what isovariance is and why we might want to study it. For the entire talk, G is going to be a finite group. I'm not going to mess with any infinite groups in this talk. I'm a little scared of them. Just to start with some notation, this is going to be pretty important notation. Let's suppose I have a G space X and a point there. And so I denote by G sub X, the stabilizer of the point X. So all of the elements in G that stabilize X. And so given that I can, for every subgroup of G, I can associate two spaces. I can associate X upper H so that those are the points in X that are fixed by H. And I can also maybe sort of less commonly associate X sub H, which are the points fixed by exactly H. So the points whose stabilizer is exactly H. All right, great. So maybe the first thing I want to note about these, okay, so maybe before I start writing more stuff, is this a good line for not to write above? Great. And how about the size of my handwriting? Can people in the back see what I'm writing? Okay, great, thank you.
Just 2.6 millimeters thicker.
Thicker, I can't actually do anything about because this is the chalk I'm given. Yeah. All right. So so maybe a note about these spaces, which is that if I have an equivariant map from X to Y, so a map that commutes with the G action, then it induces an F upper H from X upper H to Y upper H. And this is, you know, one of the things that we study the most about equivariant maps is what they induce on the fixed points. But it usually doesn't induce an F lower H from X lower H to Y lower H. So doesn't induce a map on the isotropy subspaces, X lower H. Okay, so this is where isovariant maps come in. So map F from X to Y is called isovariant. If it's equivariant, and also G sub X is equal to G sub F of X for every point in a space. So notice that just for equivariant maps, you would have a subgroup here. So the stabilizer of X would be a subgroup of the stabilizer of f of X. For isovariant maps, I require them to be equal. And a note about this is that if F is isovariant, then it does induce those FHs. So F lower h from X lower h, Y lower h. So I'll start by giving a simple example of an isovariant map. So mine and Sarah's favorite way of thinking about isovariant maps is with color coding. And so for me, this orange is going to denote points in my space that have a trivial action of the group. Oh, this blue is visible. Nice. Great. And we inherited our favorite color coding from Carrie Malkovich, who has very strong opinions about what should be which color. So here, blue are points that have free action. So I'm thinking of this point with a trivial action of the cyclic group of order 2. And then I'm thinking of this disk with the flip action of the cyclic group of order 2. And I can have a map between them that includes this point anywhere here in the fixed points. Okay, and this is isovariant. And this simple example is a part of a much greater class of examples. So, in fact, every injective equivariant map is isovariant. Okay, and so this map is isovariant, but this sort of pair of spaces can also give me a pretty easy non-example. So the map back is, from this disk to a point is, of course, equivariant, but it's not isovariant. So the way that I like to think of it is the map back sends everything to the orange point, and so therefore it sends some blue stuff to something orange. And if I want a map to be isovariant, it has to both be equivariant and preserve the colors. And so the map back, not isovariant. So sort of the slogan with which we like to think about isovariant maps is that isovariant is equivariant and stratified. So if I have a G space, I have the stratification on it given by these isotropy subspaces, and an isovariant map is exactly a map which is both equivariant and preserves that stratification. So that sort of makes it a pretty interesting thing to study. Okay, so then what Sarah and I have been doing is we've been studying the homotopy theory of G spaces with isovariant maps. And I might slip up sometimes and call them isovariant spaces. So this is sort of, we call our category, the category of isovariant spaces. But so this is the, what we're trying to do. This is the kind of homotopy theory that we're studying. So here are some reasons why we're doing this, sort of some points of motivation that are interesting to us. And of course, you know, there's plenty, but I would like to highlight sort of a couple of them. So maybe one of them is equivariant surgery theory and equivariant cobordism. So when you're studying equivariant surgery theory and equivariant cobordism theory, isovariant maps kind of show up naturally. So for example, if you are studying equivariant H-cobordism theory, you often end up having to study H-cobordisms on these isotropy subspaces. And that's hard, it turns out. It turns out that studying H-cobordisms on these is hard. And so when you're talking about equivariant surgery theory and equivariant H-cobordism theory, one thing that sometimes shows up is gap hypotheses. So you kind of want the different MHs to have very big gaps in dimension between them. And that is sort of a condition that makes isovariants and equivariants kind of match up, look no different in terms of the homotopy theory. So what we're interested in is sort of studying, not just studying the ways in which equivariant and isovariant homotopy theory are the same, but also just like what happens with isovariant homotopy theory when it doesn't coincide with equivariant homotopy theory. And so maybe then that can eliminate some of those gap hypotheses that show up over there. One really broad type of realm that motivates this is manifold topology. So, you know, that's, there's a lot to hear, but I'm going to specifically highlight the direction of configuration spaces. So, if you look at the symmetric group on n letters, this acts on the n-fold Cartesian product of a manifold by permuting coordinates. And sort of one really nice thing about this is that the isovariant homotopy type of this n-fold Cartesian product it knows more about M than just the homotopy type. So one sort of famous example of this is if I take this n-fold Cartesian product and I take only its free part, so these n tuples on which the symmetric group acts freely, this is another name for the ordered configuration space. So this is this ordered configuration space of n points inside of M that has shown up, for example, in Eva's talk, but you know, we seem to keep coming back to those. And the configuration space of a manifold knows more about than just the homotopy type of the manifold. So one really cool result by Langoni and Salvatore from about 20 years ago says that the configuration space of 2 points in the length space L71 is not homotopy equivalent to the configuration space of 2 points in the length space L72. So L71 and L72, this is sort of the simplest example of closed three manifolds that are homotopy equivalent but not homeomorphic. And the configuration space of 2 points knows the difference between those. So homotopy types of configuration spaces can be pretty powerful. And in this example, the isovariant homotopy type of m to the n kind of assembles all of this information about the homotopy types of configuration spaces of different numbers of points in M. So that's another reason why we're interested in isovariant homotopy theory. And then the third one is shorter and a bit more mysterious, which is that invariant homotopy theory is powerful, as we know. And then what happens if we make it stratified? So those are some motivations for studying isovariant homotopy types. All right. So here's some progress that we've had so far. So in 2022, Sarah proved that there is a model structure on G spaces with isovariant maps. So isovariant spaces. So maybe I'll call this category of G spaces with isovariant maps. I'll denote it isovariant top. And she also proved an isovariant Elmendorf's theorem. So this category of G spaces with isovariant maps is Cohen equivalent to some pre-sheaf category. So this was a really cool theorem. It sort of showcased a lot of ways in which the isovariant category is similar to the equivariant category, but also ways in which it's different. Sort of one problem that we had with this for our purposes, in which we wanted to study smooth G manifolds, is that smooth G manifolds are not all cofibrant in this model structure. So, yes, Ina.
Sorry, I'm having trouble placing the theorem
Yeah, this is, yes. So the question is, Ina's asking about this theorem on the model structure on isovariant spaces, and raised the question, what is the terminal object in this category? And this is indeed the bane of our existence. So the isovariant category does not have a terminal object. If I manage to get a little bit to the stable isovariant homotopy theory part of this, this makes things very confusing, because if you want to define suspension, usually you do that with like a push out of some diagram that involves a terminal object, and we don't have one of those. So the way this is solved is basically we adjoin a formal terminal object to the category, and this allows us to prove these kinds of theorems, and the problem doesn't show up again until we actually want to define a meaningful suspension. But with that formal terminal object, you can define a model structure like this. Yeah. Other questions before I continue? Yeah, Martin.
Microphone available.
In Sarah's model structure on isovariant spaces, are the weak equivalences still just the maps that induce weak equivalences on all fixed points, or do we also require them to be weak equivalences on strata?
So that's a very good question. So I'll talk more about the weak equivalences soon. So after I sort of summarize the progress, I'll say specifically what isovariant weak equivalences we consider. So we do want them to induce weak equivalences on all the strata, but we want more than that. So we want them to induce weak equivalences also on all the homotopy links between the strata, and also on sort of the higher dimensional homotopy links as well. And so I'm going to say more about that. But yeah, if you've seen some work on stratified homotopy theory, these are things that show up a lot there. And so we don't just want the strata, we kind of want all the things that connect the strata as well. Dennis, you had a question as well?
Category with a model structure What do you mean by that?
So I didn't say exactly what this pre-sheaf category is, but Elmendorf's theorem says that G spaces, so equivariant homotopy theory, is Quillen equivalent to a category of functors from the orbit category to spaces. And here we have something similar to that. So instead of functors from the orbit category to spaces, we have something that's more like functors from what we call the link orbit category to spaces. So basically, if you want a name, this is some small category LG op to topological spaces. And this is sort of given like a diagram projective model structure type of thing. Yeah. Okay. So I've been saying a bunch of stuff about model structures, and I am aware that not everybody works with model categories all the time. So if you don't work with model categories, I want to just give a few highlights of like what is important to us when we work with model categories. So the most important thing is that model categories help us organize homotopy theory. And so weak equivalences, the stuff that we choose to regard as sort of equivalences in our category, that's maybe the most important aspect of a model structure. But we also really care about cofibrant objects, so ones that are built out of cells, and fibrant objects, which have this kind of lifting property with respect to cell inclusions. And so some of these theorems are going to have cofibrant and fibrant in them. Basically, what we want is to be able to study objects that we're interested in in a model structure, we want those objects to be cofibrant and fibrant. So the problem that arose here is that smooth G manifolds, which we would very much like to study, are not cofibrant and fibrant. They're not built out of cells, so they're not cofibrant. And this is not like you don't need to come up with obscure examples for this. So even if I take this rather simple manifold, I take a disk with the cyclic group of order 2 acting by rotation by 180 degrees. This one is not built out of cells in this sort of pre-sheaf model structure on isovariant spaces. And the same is true for like the 2-sphere with rotation action. So those are really like fundamental smooth G manifolds that we would not really be able to study well using this model structure. All right, so then we set out to find a better way to specifically study smooth G manifolds with isovariant maps between them. And so what we proved is that there is a weak model structure on G spaces with isovariant maps in which smooth G manifolds are cofibrant and fibrant. So this is slightly weaker than actually having a model structure. There were some really gnarly issues that came up when trying to prove that it's a model structure, but it is a weak model structure, and that enabled us to do all that we wanted to do with it. And in particular, one thing that we managed to prove using this is an isovariant Whitehead's theorem. So if you remember from maybe your first couple of courses in algebraic topology, the Whitehead's theorem tells you that weak equivalences between CW complexes are homotopy equivalences. And so similar isovariant thing also holds. So if f from M to N, where M and N are smooth G manifolds, is an isovariant weak equivalence, then it's an isovariant homotopy equivalence. So couple of things about this. Isovariant homotopy equivalence means what you want it to mean. So homotopy equivalence, we have maps in both directions. Both their compositions are homotopic to the identity. Isovariant homotopy equivalence, just put isovariant everywhere in that definition. So isovariant maps, their compositions in both directions are isovariantly homotopic to the identity. So great. Isovariant weak equivalence, that is something that that I'm going to say more about now. So maybe the next step is saying a little bit more about what isovariant weak equivalences are. So remark, if we have F, an equivariant map, this is an equivariant weak equivalence. If and only if F upper H, which is, I can think of it as equivariant maps from G mod H to F, are all weak equivalences in topological spaces for all subgroups H. So this is how we test that that an equivariant map is a weak equivalence. And isovariantly, we consider F lower H, so isovariant maps from G mod H to F, and these go between X lower H and Y lower H. But also maps from higher dimensional simplices. Which we denote delta blackboard bold H. Okay.
H cross the G mod H.
So I'm gonna say a little bit more about that right now. Yeah. Yeah, so it's a little more complicated than that. So here by H, I mean a chain, a strictly increasing chain of subgroups of G. And here are some examples of what those delta H's are. So if H is just a single subgroup, H, then delta H is just G mod H. So the space of isovariant maps from this zero-dimensional simplex X is just the isotropy subspace X lower H. And let's go one dimension up. So the space of isovariant maps from delta H less than K into X. You can think of this as a space of paths. So I'm taking paths from the interval into X that start in the K isotropy and continue in the H isotropy. So you might, if you've seen a little bit of stratified homotopy theory, this is a version of what can be referred to as exit paths. You know, on the face of it, this is a path space. We're starting. I don't think so. I don't think I do. Yes, start out with a bigger group, so therefore the smaller space. So you're going from a smaller stratum to so from a lower dimensional stratum to a higher dimensional stratum. Yeah, no, it's eternally confusing to me as well, but I'm pretty sure this is yeah. No, it's the contravariance here is always confusing. So these are paths that go from lower dimensional stratum to a higher dimensional stratum. And maybe another thing that I want to say about this kind of thing is that if X is a smooth G manifold, then this doesn't have to be this infinite dimensional path space kind of thing. If X is a smooth G manifold, this is really just like a punctured tubular neighborhood of this lower dimensional stratum. And so this is really like a manifoldy type of thing. Like you're taking a tubular neighborhood of this inside of this, and you're removing this thing itself. And so, some kind of like spherical bundle type of thing, and it ends up being really nice. So those are the examples that I wanted to give with these isovariant simplices. Generally, there's some kind of quotient of like n simplex times G by some identifications. I'm not going to go into exactly what those are. Here's the definition. So an isovariant map F from X to Y is an isovariant weak equivalence if when you map out of each of these simplices, you get weak equivalences of topological spaces. For every strictly increasing chain of subgroups. So I'll say that for X and Y nice, by which I mean cofibrant and fibrant, it's enough to check the zero-dimensional simplices and the one-dimensional simplices. So that's one of the reasons why I only told you about those two, because when you're talking about X and Y that are cofibrant and fibrant, to know that something is a weak equivalence between them, you only have to check the zero-dimensional simplices and the one-dimensional simplices. Okay. So this already allowed us to conclude things about isovariant maps between smooth G manifolds. So let's let M be a compact smooth G manifold. So it could have boundary if it wanted to. And we need some mild dimension hypotheses here. If we have a map F from M to M, which is equivariantly homotopic to a map without fixed points, so by fixed point, I mean a fixed point of the map F, not of the group action. Then F is also isovariantly homotopic to a map without fixed points. So developing isovariant homotopy theory in a way in which smooth G manifolds are nice allowed us to then apply Klein and Williams homotopical intersection theory in this context, and show exactly when we can eliminate fixed points from an isovariant maps in an isovariant way. And so this is a theorem in which isovariantly things end up behaving surprisingly similarly to how they behave equivariantly. So this is sort of like a step in the study of how those two categories are similar and how they're different. But these dimension hypotheses are much, much weaker than the gap hypotheses that usually show up when you talk about isovariant and equivariant coinciding. So this was sort of surprising to us. So in the last 15 seconds or so, I just want to mention that we've also been working towards isovariant stable homotopy theory. So some of our most recent theorems. Posted on the archive like a week and a half ago, are an isovariant Blakers-Massey theorem. So if you have an isovariant homotopy push-out square, how close is it to being homotopy pullback square? And also an isovariant Freudenthal suspension theorem. And I would say the most difficult part about this isovariant Freudenthal suspension was defining suspension in the isovariant category. So this is related to the problem that Ina mentioned with the terminal object. So yeah, so we're hoping to sort of learn more about what happens in isovariant stable homotopy theory. Like, is it the same as equivariant stable homotopy theory? Can we suspend by representations? Like that's really important in equivariant stable homotopy theory, and we want to see if that happens isovariantly as well. We are going to think about isovariant Bredon homology. So how can we define a sort of correct homology theory for isovariant spaces? And then sort of maybe look back towards manifolds and see if we can say things about isovariant Whitehead torsion using isovariant stable homotopy theory. Okay, I'll stop here. Thanks.